second unit has been completed. So can you see the presentation?
Yes, ma'am,
Yes,
it is.
ma'am.
So it is basically time response characteristics. That is unit 3. Okay. So basically, what we are concerned in the time response of control systems are the poles and zeros configuration. Okay. So poles and zeros of a first order system, you can understand with the help of this example that we have a block with transfer function s plus 2 upon s plus 5. The input is rs, output is cs, and the transfer function of the system is gs. So if you plot the pole zero configuration, you can see that what is pole? Pole is basically denominator of the transfer function equal to substituted equal to 0. So when you substitute the denominator s plus 5 equal to 0, you get a pole at s equal to minus 5. And what is a 0? 0 is a frequency at which the transfer function becomes 0. Okay, so what you do, you substitute the denominator of the transfer function equal to 0. So s plus 2 equal to 0 gives you a 0 at s equal to minus 2. Okay, so these values are plotted in the complex s plane using cross symbol for the pole and a circle, small circle for a 0. Okay, and to show how the pole and zero affect the system time response, let us find the unit step response. What do you mean by unit step response? Is this that we take rs equal to 1 by s. Okay, so unit step is basically the Laplace transform of unit step is 1 by s. So you can substitute cs by, because cs, if you try to find out the output cs, it will be gs into rs, and rs is 1 by s and gs is s plus 2 upon s plus 5. So cs becomes s plus 2 upon s into s plus 5. So if you take the partial fraction, if you do the partial fraction expansion of this linear transfer function, then this is the procedure by which we find the linear fractions of this polynomial, right? So a upon s plus b upon s plus 5. So you have to find out the value of a and b. If you do this, you are familiar with how to solve such linear factorization. So if you do it yourself, then you will find that a and b will get, you can try it out yourself, or I have given you the procedure. What you do, you take s plus 2 upon s plus 5 and substitute, take the value when s equal to 0, right? Because for this factor, we substitute, we don't take this. For this we'll take s equal to minus 5, and for this we'll take the limiting value for s equal to 0. So a is basically 2 by 5 and b is basically 3 by 5, right? And if you take the inverse Laplace transform of this expression, you get this expression ct equal to 2 by 5 plus 3 by 5 e to the power minus 5t. Do you agree with this? I want you to take down the notes, start taking down the notes. Take out your register, control register, put today's date and take notes. All right, I'm giving you time. So basically, this is the um, pole zero configuration. If you take the input pole, right? Input pole is that because the input is 1 by s, right? So you have a pole at origin, So that determines the input pole. And the system 0 is at s equal to minus 2, and system pole is at s equal to minus 5. So output transfer function Cs is 2 by 5 upon s plus 3 by 5 upon s plus 5. And the output time response is basically this, we have derived it. So 2 by 5 plus 3 by 5 e to the power minus 5t. So if you draw some conclusions, that is, at the pole at s equal to 0 of the input function generates the form of the forced response, right? Because this is the forced response 2 by 5. That is, a step input generates a stepped forced response. Okay. And the pole at s equal to minus 5 of the transfer function generates the form of natural response. That is, a real axis pole at 5 generates an exponential of e to the power minus 5t, this term. Okay. The farther to the left the pole is on the negative real axis, the faster the exponential transient response will decay to 0. Right? This is the first and foremost conclusion, that as you move away from the imaginary axis or j omega axis, what you do, what we get is we see if the response is like this, the response will decay to 0 value faster, right? And the zeros and the poles generate the multitude amplitude of both forced and natural responses, right? 2 by 5 and 3 by 5. So this can be seen from the calculations of A and B, right? So some exceptions on poles and zeros depend on dependent time response characteristics. The form of the nature of the forced response is dependent, but not only on the input poles. The form or nature of the forced response depends on the transfer function poles, which are common to the input poles. And the form or nature of the forced response depends on the possible zeros at the origin in the transfer function. Okay, so you can take another example and you try to solve it yourself by uh, following the same procedure as I have told you in the previous example. So please do it yourself, and I am giving you the solution also. I would like you to write this in your notebook. In this expression of final transfer output response, so it is one of the term is constant and the other are having some exponential coefficients with it. So the term which is constant is called the forced response, and the term with exponentials are called the natural response. So each pole of the transfer function generates an exponential as part of the natural response. The input pole generates the forced response. Okay. So what are the definitions? So suppose we are having a system, first order system with transfer function a upon s plus a. So the performance specifications of first order system without zeros. First order system without zero can be described by the transfer function shown in the figure. Right? So it is basically CS is RS into GS. So it is A upon S into S plus A is the step response of the first order system. Okay, so if you take the inverse Laplace transform, you will get forced response CFT plus CNT, natural response. So forced response is basically 1 and natural response is minus e to the power minus 80. So now let us examine the significance of the parameters A by evaluating the step response at t equal to 1 by A. So CT at t equal to 1 by A. So you replace t by 1 by A here. So you take 1 minus e to the power minus 80 at t equal to 1 by A. So it becomes 1 minus 0.37, because e to the power minus a minus 1. So e to the power minus 1 is minus 0.37. So 1 minus 0.37 is 0.63. So this is basically time constant. So 1 by a, we call it as the time constant of the response. It is the time taken by the response to rise to 63% of its final value, which is unity in this case. The reciprocal of the time response a is called the exponential frequency, which determines the initial slope of the response. Right? So this is very important definition of a control system, and it is normally always asked what is pole zero, what is time constant, right? So I want you to write down this definition of time constant in your notebook. So time response, if you plot graphically, you will get this plot. The time constant can be considered as a transient response specification of a first order systems, since it is related to the speed at which the system responds to a step input. Okay, the farther the pole s equal to minus a from imaginary axis, the fastest the transient responses, as I have told you earlier also. So this is basically ct versus t, and this is the first order time response. Initial slope is 1 by time constant, which is equal to a, and this is the 63% of the final value. Final value we are taking as 1 at t equal to 1 time constant, right? So at this point we call it as tr, transient time constant, huh? And this is, suppose we are having 1 by a here, 2 by a here, 3 by a here, 4 by a here. So it is basically at 4 by a we get the settling time, so rise time tr is the defined as the time for the response to go from zero point 0.1 to 0.9 of its final value, and it is given by 2.2 upon a. And settling time is the defined as the time for the response to reach and stay within 2% of its final value. It is given by 4 by a. And graphically, it is represented like this. So I want you, all of you, to take the plot this graph in your notebook and write down the definitions of rise time and settling time. This is basically the first order time response, and it is not possible to or practical to obtain a system's transfer function analytically. So laboratory testing can be performed to determine the transfer function of a first order system. With a step input, we can measure the time constant and the steady state value from which the transfer function can be calculated. So assume that the system has unit step response as shown in the figure. It is a first order system because of no overshoot and non-zero initial slope, right? So this is the shape of the first order system. Suppose we are having this with us. Then suppose that the system transfer function is given by gs equal to k upon s plus a, whose Laplace transform will be k upon s into s plus a. So it is basically k by a upon s plus minus k by a upon s plus a. So if you take the inverse Laplace transform, it is ct equal to k by a minus k upon a e to the power minus at. So where k and a are to be determined. So from the response, which is graphically presented with us, so we can calculate, we can see that the final value is 0.72, this one. If you see that the final value is 0. Approximately equal to 0.72, then the time constant is evaluated where the curve reaches 0.63 into 0.72, which is 0.45. So at this point, what is the value of time? So it is, if you graphically calculate this, you will get a time of 0.13. Therefore, a equal to 1 upon 0.13, that is 0.7. However, k is found by k upon a equal to 0.72. So k gives the value of 5.54. Therefore, gs becomes 5.54 upon s plus 7.7, which is the transfer function of the system. So this is how we calculate the transfer function from the graphical or laboratory uh, time response of the given system. So I want you to note down the procedure. Time response of a second order system. These are the numerical examples. So you have second order system is described by denominator having second order. So s square plus as plus b will generate a second order system. So if you take the Laplace, the actual value of b and
रि-
a,
वो रिप्रेजेंट नहीं हो पा रहा है इसमें.
present नहीं है. Okay, let me. Is it now visible?
Yes, ma'am.
So, all right. So this is basically time response of a second order system. So second order system is described by this generalized equation. And if you substitute the value of b equal to 9 and a equal to 9, then you get this value. And if you take the pole zero configuration, you will get a two poles. Because it is a second order system, you will get two poles. And this is an exercise to you to calculate the poles of this system. Find out the pole and then plot the response. Do it yourself. I'm giving you time. This exercise, and I'm creating a window on your Google Classroom. You have to upload the solution by taking each example.
है.
हाँ हाँ, आप लोगों का मैंने वो असाइनमेंट क्रिएट कर दिया है. आपको इस पे ये जो अभी क्वेश्चन दिया है इसका सॉल्यूशन अपलोड कर दीजिएगा. यू कैन लॉग आउट. Classroom assignment, question 1 unit 3.
इसमें
Okay.
वो डायनेमिक आ जाती है, उस क्लास है उस वक्त.
हाँ, कुछ नहीं करना है. 1 घंटे का टाइम दे दिया मैंने आपको, उसके बाद कर लेना.
क्लास है मतलब कंटिन्यू.
हाँ, तो 1 बजे से तो नहीं है ना.
फिर लैब है उसके बाद.
लैब कंट्रोल की तो है. चलो टाइम बढ़ा देती हूँ मैं. ट्राई करो, फिर कंट्रोल की क्लास में तो मैं आऊंगी ना. लैब तो मैं ही लूंगी ना.